Hi, we will continue the controllers video. So in this video we will see proportional and integral controller. We call it as PI controller. So it is similar to PD controller. So where we had discussed in the previous video, it was K was a proportional constant and tau S was the proportional, this is a derivative term. So now we have a proportional constant which is Kp, or you can just say it as simply K to go in line with whatever we had it for PD controller. And for integral it is 1 over tau S, so it's 1 over tau S, and we are just retaining the same transfer function as we considered in the previous case. So let us try to understand, for a value of K is equal to 10 and tau is equal to 0.04, what is the transfer function we're going to get after PI controller. So without PI controller, without this controller, we know what is the value of overshoot, settling time, and these are the values without considering the controller. So these are the values what we have without controller. Now we shall consider PI controller, then try to identify what is the impact of that PI controller on all these parameters. So now let me just do this now. So does this become 10 plus 1 over 0.04? Yes. So this is my tau value, and this is multiplied by 10 into, of course it is a square plus 6s plus 8. This is my g of s into h of s, which I can simplify this and write it as, so it is what is this, will it not become 0.4s plus 1 divided by 0.04? Yes, this is actually into 10 is there, and this will become a square plus 6s plus 8. Then this can be further written as, so can I write it as what will be this now? I will, okay, now when I just multiply this with this, will it not become, what will be that value? Will I be getting as, okay, let me just take out, okay, now this 0.04 is there, so I take out 0.4 outside, then this will become, so, and into 10 is also there. I will make this, so it is now s plus 1 over 0.4 divided by, so I have 0.04 here, so it is s into a square plus 6s plus 8. So here it is 4 divided by 0.04, and s plus 1 over 0.04 is 2.5, and this is s into a square plus 6s plus 8. Correct? So what is 4 by 0.04? 4 by 0.04 becomes 4 divided by 0.04 is 100. Correct? Okay, now I have this g of s into h of s as 100 into s plus 2.5 divided by s into a square plus 6s plus 8. So this is g of s into h of s after introducing a proportional and integral controller. So once you have this as g of s into h of s, I want to find what is c of s by r of s. So what is c of s by r of s? From this g of s h of s with h of s as 1, so c of s by r of s will become 100 into s plus 2.5 divided by, will it not become s cube plus 6s square plus 8s plus 100s plus 250, correct? Now I'm just multiplying this 100s and this 100 into 2.5 is 250, so that is added to this term. So this ultimately becomes CFS by RFS now becomes 100 into s plus 2 and what is this, s cube plus 6s square plus 108s plus 250. So this is my characteristic equation. Let me try to find out what are the dominant poles from this, because I want to find out MP, settling time and settling time for a unit step input. So this is my u of t. So for that I need to know the second order system. Second order system from a third order system can be obtained by identifying the dominant poles. Let me repeat. So this is a third order system. From this third order system, let me identify the roots of it and then later identify the dominant poles of this. So I can actually find out what are the roots of this. Now it is 100 into s plus 2, so it is s plus, so what are the roots here now? So let me find the roots. 1, it's of order 3, it is 1, 6, 108, 08 and 250. Okay, these are my coefficients. Okay, now it is, okay, the roots are minus 2.51 and the other one is minus 1.74. it's a complex one, plus or minus j 9.8. So these are my three roots. So two are complex, one is on the real axis. If you see this is the one which is having lesser real value, so this happens to be my dominant pole. So now the roots, okay, I can write it as s plus 5.1 and s plus 1.74 plus or minus j 9.8 is my poles. So out of which this is my dominant poles, so I can take out dominant poles. It is now s plus 1.74 plus or minus j 9.8. So of course this is nothing but s plus 1.74 plus j 9.8 and s plus 1.74 minus j 9.8. If you multiply these two, I will get, of course it's exactly s square plus twice of this. So what is twice of 1.74? 0.74 into 2. Sorry, I need to bring it to 1.74 into 2. It is now 3.48s plus, now it's actually s square plus twice of 1.74, yes, and 1.74 whole square plus 9.8 whole square is equal to 0. So now I have to do 1.74 square plus 9.8 square, it is 99 point something, so it is 99.06 equal to 0. This is my characteristic equation, or sorry, this is my dominant poles equation. So I will equate this to s square plus 2 zeta omega ns plus omega n square. So when I am equating the omega n and zeta, from which I can find what is MP and TS. So what is omega n? Omega n is actually root of 99 point. Of course it's root of 99. Let me find out. Root of 99 is 9.95. And what is zeta? Zeta is actually 3.48. It is 3.48 divided by twice of 9.95. It's like, okay, quotient of s divided by 2 into omega n. So 2 into omega n is, it is this much, divided by 2 into 9.95. so it happens to be 0.174. so for that MP happens to be, how much is MP? So MP is coming out to be for 0.174. okay, let me find out. It is e to the power of minus 0.174 into pi divided by under root of 1 minus 0.174 square, close. See, now it is 57.4% is my MP. TS is how much? TS is, it is 4 by zeta omega n. So it is now 4 divided by zeta is 0.174 multiplied by omega n is 9.95. See, now it is 2.31 second. So let us compare with the, of course, let us also identify how much is ESS. So now this is my GFS. So now GFS has got a term S in the denominator, meaning, so there is a pole at the origin. We know that when you have a pole at the origin, so this is type 1 system. For type 1 system, for a step input, we know that ESS is equal to 0. For a type 1 system, for a input which is step, I am going to get steady state error as 0. So now steady state error now is 0. So we have okay, let me just compare the previous here. So let me just write it here only. This was without any controller. We had it as so and so. So now let me have a PI controller which has got 10 plus 1 over 0.04 S as its tau and the K values. And what is this MP? We got it as around, so MP is 57%, settling time is 2.31 second, but ESS is 0. So of course you are getting a larger overshoot, it will take larger time, but ultimately the steady state error becomes 0. Steady state error becomes 0 here. So this is the advantage of having a PI controller. Of course in the previous PD controllers we saw that there was some error, there was some steady state error, even though when you increase PD, when you replace P by PD, so you had some error, but when you have a PI controller, the ESS becomes totally 0. ESS becomes totally 0. So this is the advantage of having, of course, at the cost of increased MP, and TS is also increased. Okay, just give me a minute. Okay, let us continue with, of course, as we saw in this PI controller, without controller we had an overshoot of 4.32%, and the settling time was 1.33, and it was having a steady state error of 0.44. But when we actually did with a PI controller with a proportionality of 10 and a time constant of 0.04. Let me just clarify this. This is 1 over tau I into S. This is actually 0.04 into S. So this was intentionally taken 0.04. So because of so it should ensure that it should properly give a response also. We cannot take some random values. So now for this time constant of your integral controller, we had a overshoot of 57%, which is more than 10%, almost 12%, and settling time is also more. Very importantly, we have a steady state error of 0. So this is the major advantage of this PI controller for this transfer function. If the transfer function differs, then of course it varies from case to case. It varies from transfer function to transfer function. these values of 10 for this and then 0.04. It's not fixed, it just varies with the system transfer function. Now let us try to see how do we include all the three, that is proportional, integral as well as derivative. We call it as PID controller. You can see there is a proportional, there is a derivative. We can see now it is tau d into s. Can you see this is 1 over tau I into s. So you have a s, you have a 1 over s term. So all the things are now added, they are in parallel. So now let me just take it something like this. You have it as 10. So you can just think of you are having one more, maybe 0.1 s. So let us have this as plus. This is your derivative controller, this is d, this is actually p, and you have it as 1 over 0.04 yes. So this is actually integral, it is PID controller. So this is your, okay, let me take that feedback. This is RFS. So we have that same system, 10 by s plus 2 into s plus 4. So I'm just having the same thing here. So this is what we have, this is minus. So let us try to find out what is this block multiplied by this block. So this block happens to be, okay, now what we have is 10 plus 0.1 s plus 1 over 0.04 s. So this is this block. So let me try to simplify this. Is it not 4? All we have is 10 into 0.04 is actually of course 0.4s plus 0.004 s square plus 1 divided by 0.04. Yes, and of course this is multiplied with 10 by, this is what we are talking about, GFS into HFS. So it is s square plus 6s plus 8. Now if I further simplify this, let me make this s square quotient as 1. So if I take out 0.004 outside, and this will be s square plus, so what is 0.4 divided by 0.004 is actually 100 yes, plus, so it is 1 divided by how much? 0.004, that is 250. This is 250 into 10 divided by 0.04 yes into s square plus 6s plus 8. So what you have is 10 into 0.004 divided by so 0.004. So now do we have a transfer function? So now this into this is 0.04, this is also 0.04, so this will go off. So what is your GFS into HFS of the PID controller, including PID controller? This becomes s square plus 100s plus 250 divided by s into s square plus 6s plus 8. So this is my GFS into HFS. So from this, if you want to find CFS by RFS, it will be the numerator will be the same. It is s square plus 100s plus 250, but the denominator is s cube plus 6s square plus 8s plus s square plus it is 100s plus 250. So this denominator becomes, so overall CFS by RFS will become what? S square plus 100s plus 250 divided by s cube plus 7s square plus 108s plus 250. This is my transfer function. So I found the roots of this. So roots of this denominator happens to be s plus 2.58 and s plus 2.20 plus or minus j 9.57. You can verify this. So find the three roots of this. One of them is minus 2.58, other one is minus 2.2 plus or minus j 9.57. So these are the roots for these. Okay, now out of these three poles, these two are dominant poles. So the dominant pole quadratic equation becomes s square plus 4.4s plus 96.42 equal to 0 is the dominant poles equation. If you are equating these two, that s square plus 2 zeta omega ns plus omega n square, we will end up with, so what is that we're going to end up is, so we will have a omega n of 9.81. So what is this 9.81? It is under root of this, and zeta happens to be 0.224. So let us try to find out what is Ts and this. So what is Ts? It is 4 by zeta omega n. So 4 by zeta omega n is 4 divided by zeta is 0.224 into 9.81 radian per second. So it is now 1.82 second. Whereas MP is, what is MP? MP is exponential to the power of minus 0.224 into pi divided by under root of 1 minus 0.224 square. Oh, natural means I think I just put in one more extra parenthesis. Let me delete that. Oh. Exponential minus of 0.224 into pi divided by the root of 1 minus 0.224 square. 224 square, close. Yes, it is 0.4857. So it is 48%. We can find GFS into HFS has got a S term. This is also type 1 system. ESS is 0. So if you compare, so now we can just make a fair comparison. Let me do that. So maybe let me write it here separately. What is for different controllers and for the same transfer function, for a system having a planned transfer function as 10 by s plus 2 s plus 4, if the controller is P, PD, PI or PID. So for all the three we actually found out. This is unity controller. If the controller is not there, this is your controller. If the controller is not applied, so what is your MP, settling time and ESS? When it is not there, so now if you can see, we had the values as 4.32% and it was 1.33 second, and ESS was 0.44. So when you had only the proportional controller with K is equal to 10, what was this? You can see now it was 38.8 and the error was, the settling time was still 1.33, but error got reduced to 0.074. When we had PD controller with this as 10 plus 0.1, yes, this is your proportional, this is derivative. We had it as 32.6. 32.6 was your overshoot, and this was 1.14, and ESS got reduced to, of course, ESS was almost the same. It has reduced the overshoot and the TS for these values of proportional time constant, proportional value and time constant of derivative controller. For PI, when we consider this is now 10 plus 1 over 0.04 s. Okay, for this specific value, we had the overshoot as 57%. The time was 2.31 second, and ESS is absolutely zero. ESS is absolutely zero. More overshoot, more time, more settling time, but ESS is zero. When we did the last one, that is PID controller, which has got 10 plus 0.1 s plus 1 over 0.04 s, all the three included, we had an overshoot of how much? 48%, and we have a settling time of 1.82 second, and ESS is zero. So if you can see, PID controller has got of course ESS 0 and better settling time than PI controller, and of course, so this is the advantage. But for PD controller, you have some ESS, but overshoot and the settling time are less. So depending on your application, you can go for either PD controller, P controller, or PID controller. So PD controller has an advantage of reduced overshoot and reduced settling time, and almost same, of course, same ESS. It's not almost same, it's same ESS. But here ESS is 0 for PI or PID controller. Of course, this is, I'm very specifically saying, this is for a system which is a type 0 system, and we are considering for ESS, it's a step input. So this, if the input is different, if the type of the system is different, all these things will change. Okay, this is what about the controllers. Of course, usually what we actually did was, we took the values of Kp, tau d and tau I, and we found out what are the time constant parameters along with the steady state error. But actually in the designs, we are supposed to find Kp matlab the proportional controller value, and the tau d and tau I for a given specifications. So we are actually supposed to find this. So we are actually doing the forward engineering. We have to do the reverse engineering when you are doing the design of a controller. Thank you.